Our world is filled with matter. Everything you see, touch, and feel, and even things that are invisible, such as the air around us, are all made of substances called elements. Elements are the building blocks of all matter. Some are very familiar to us. Copper, for example, is an element which everyone knows. It is a metal easily recognized by its color. Copper has many uses, such as for making electric wire, tea kettles, and of course, pennies. Helium is a common gaseous element. It is known to anyone who has bought a balloon at the zoo. Helium is less dense than air, so balloons filled with it rise up and need to be held by a string.
People in ancient times thought about elements. Aristotle, a Greek philosopher who lived more than 2,000 years ago, taught that only 4 elements were used in various combinations to make everything in the universe. He identified these elements as earth, fire, air, and water. To illustrate his point, he used this famous example. When a piece of wood burns, you can see the fire escaping from it as flames. The air from within the wood escapes as smoke. When the wood has been completely burned, the ashes that are left represent the earth. So, wood is made of fire, air, and earth. To people living at the time, this made very good sense, and Aristotle's ideas about the 4 elements of matter were widely accepted.
One thinker believed differently than Aristotle. Democritus taught his students that matter was made up of small particles he called atoms, which he derived from the Greek word atomus, which means cannot be divided. He explained that if a loaf of bread were broken into pieces, even the smallest crumbs we can see are still bread. But if you could continue to divide the bread into smaller and smaller pieces, eventually you would have to stop when you had only one atom of bread. That atom could not be further divided. Democritus's ideas were rather close to what is now thought to be true about matter. For 2,000 years after his death, people continued to believe in the 4 elements that Aristotle proposed.
Our modern understanding of elements began hundreds of years ago, when alchemists tried to discover a method to change lead into gold. Alchemists were convinced that all matter was made of only a few basic substances, and that by rearranging these elements, one substance could be turned into another. What they hoped to do was change a seemingly worthless material, such as lead, into a valuable material, such as gold. Of course, alchemists also tried to find the secret to eternal life, and to cure disease, with such medical wonders as the stomachs of frogs. Though their ideas may seem strange, we must admit that they had an important effect on science, as their work led to what is now known as chemistry. By the way, it's possible to change one element into another, but this requires sophisticated equipment and the ability to change the number of protons, neutrons, and electrons in an atom. To make this kind of change is usually far more expensive than the resulting value of the new element used.
When we view our world, we see a wide variety of matter made from what seems to be a countless number of materials. The fact is that everything in our world is made of fewer than 100 elements combined in various ways. Elements are basic substances that cannot be broken down into simpler substances by ordinary chemical or physical change. Scientists have discovered 92 elements existing in nature. They have also produced some synthetic elements in their laboratories, so the total number of elements now known is 112. Sulfur is an example of a natural element. It is a yellow solid which can be found in large underground deposits in Texas and Louisiana. Plutonium is a synthetic element. It cannot be found in nature, but it can be made in a nuclear reactor.
In 1808, John Dalton proposed new ideas concerning atoms. Using the ideas of Democritus, he described atoms as tiny particles that could not be divided. He thought each element was made of its own kind of atom. Dalton had no idea of the size of atoms or how they were constructed. In time, evidence began to emerge suggesting that atoms are made up of even smaller particles, called the electron, proton, and neutron. The discovery of these particles makes an interesting story.
J. Thomson, an English scientist, discovered the electron, the first of these particles, in 1897. Electrons are particles which are smaller than atoms and which have a negative charge. Thomson knew that atoms themselves were neutral in charge, but he couldn't find the positive particles that would balance the negative charges of the electrons. It took other scientists to discover them.
Ernest Rutherford conducted an important experiment in 1911 that helped show the structure of an atom. He knew that atoms had positive and negative particles, but he didn't know how these particles were arranged. Rutherford took a radioactive substance that emitted a steady stream of positively charged alpha particles. He put this radioactive material into a lead box that had only one very small hole so that the beam of particles could be aimed. He then took a thin gold foil and placed it between the radioactive material and a detecting screen, which was made up of a material that glows when electrically charged particles strike it. He found that most of the particles went directly through the gold sheet and struck the detection screen. He moved the screen around to different locations and discovered every once in a while a particle bounced back from the foil as if it had hit something. This only happened to about 4 particles in every 10,000. Rutherford concluded that the atom was mostly made up of empty space, except for a dense central region which became known as a nucleus. In the nucleus were the positively charged particles, which were called protons. They would cause the positively charged alpha particles to bounce back, since same charges repel each other. It was a surprising discovery which amazed the scientific community. Rutherford said that the outcome was like watching a bullet from a gun strike tissue paper and bounce back. He pointed out that the atom resembles the solar system, with the nucleus in the center and electrons orbiting around, just as planets orbit the sun.
People wondered why electrons, which have a negative charge, weren't pulled into the nucleus, which had a positive charge. Remember, the opposite charges attract each other. In 1913, Niels Bohr suggested an answer to that question. He thought that electrons traveled only in fixed paths as they traveled around the nucleus. The paths were a certain distance from the nucleus, and the electrons were required to follow these orbits, which he called energy levels. This became known as Bohr's atomic model. Scientists still use this model when they draw circles to represent the number of electrons in an orbit, but the modern view of the electrons has changed greatly. Today we think of the electron as not occupying specific orbits or paths. Instead, the electrons fly around the nucleus in random paths, and it is impossible to show where they are at any given moment. The new model shows an electron cloud where electrons travel rapidly throughout the atom. The dark areas of the cloud are areas where the electron is predicted to be more likely found. The energy levels still exist in this model, and each level can hold a certain number of electrons. For example, the first level can hold 2 electrons, the second can hold 8, and the third energy level can hold 18.
During the early part of the 20th century, scientists were able to perform experiments to determine the amount of positive charge in the nucleus of an atom. Every proton has one positive charge, so it was possible to determine how many protons are in each atom. All protons are exactly alike, just as all electrons and all neutrons are alike. The thing that makes each element unique and different from every other element is the number of protons in the nuclei of its atoms. The basic structure of an atom includes the nucleus and electrons that orbit around it. The nucleus is made up of the protons and neutrons. The neutrons have a neutral or no charge. Protons and neutrons are approximately the same mass. Atoms have the same number of protons and electrons, so that the overall charge of the atom is neutral. The number of protons in an atom is called its atomic number, and the total of protons and neutrons is its mass number. When we say that each element is made up of its own kind of atom, we mean all atoms of a certain element have the same atomic number. They do not always have the same mass number. For instance, there are 3 forms of hydrogen atoms. Most hydrogen atoms have 1 proton, 1 electron, and no neutrons. However, some have 1 proton, 1 electron, and 1 neutron. Another form of hydrogen has 2 neutrons in its nucleus. So there are 3 different versions of hydrogen. Each has 1 proton and 1 electron, but the number of neutrons varies from none to 2. These 3 versions of hydrogen are called isotopes. All elements have isotopes. Every element has a property called its atomic mass, which is the average mass of its atoms after consideration is given to the fact that some isotopes are more common than others.
Now here's a rather complicated idea. Matter is mostly empty space. That means that even things that appear to be solid are actually mostly empty. That's because atoms are themselves mostly empty space. The diameter of an atom is about 100,000 times larger than the diameter of its nucleus. There is nothing between the nucleus and the tiny electrons spinning in orbit. To understand this point, imagine a huge mountain. If we could remove the empty space within every atom that makes up that mountain, the mountain would fit inside a quart-sized jar.
Often people question how it's possible to know something about an object that you can't even see. Well, think back to all the times you successfully figured out what was in a wrapped present or sealed container. You couldn't see through the wrapping, but you used other senses and powers of observation to supply you with the necessary information to make an educated guess as to the contents.
In 1869, the Russian chemist Dmitry Mendeleev organized the 60 elements known at the time into a table. He first arranged the elements by atomic mass, and then he placed those with similar chemical properties in columns. He called this the periodic table of elements because elements with similar chemical properties appeared at regular intervals. Mendeleev was so convinced that the elements occurred periodically that he left a few empty spaces in the table for elements that were unknown at the time. Years later, the elements were discovered as he predicted.
In 1913, Henry Moseley, a physicist, suggested that it is the atomic number rather than the atomic weight that identifies an atom's properties. So he proposed a slight change in the organization of the periodic table. Instead of grouping the elements by atomic weight, he used atomic number. Remember that the atomic number is the number of protons and electrons in an atom.
The periodic table can tell us a great deal about each individual element and the family to which it belongs. Each element has its own box with specific information supplied. In the center is the symbol for the element. The symbol is a 1- or 2-letter abbreviation. Scientists want a quick way to represent elements, so a symbol has been given to each. Under the symbol is the name of the element. At the top of the box is the atomic number, which tells the number of protons in each atom. At the bottom is another number. That is the atomic mass of the element. Notice that the atomic masses are not whole numbers. Recall that this is because they are averages.
If you look closely at the table, you'll see a zigzag line on the right side. This line separates the metals from the non-metals. All metals are located on the left side of the line. Non-metals are found on the right side, with the exception of hydrogen, which is located in the first column on the left. About 4/5 of all the elements are metals. Metals are easy to recognize because they're shiny. All metals are good conductors of electricity and heat. Also, they can be made into different shapes without breaking. For instance, aluminum can be made into cans, hubcaps, or a very thin foil. Gold and silver are two of the very best conductors of electricity. That's why expensive audio and video equipment might use gold-coated cables for the very best conduction of electrons. Let's look at some of the more common metals. Aluminum is no stranger. We use it to make foil for wrapping sandwiches. Aluminum is also used for making beverage cans and lightweight engines. Tin is best known for its presence in tin cans. Actually, tin cans are mostly made of steel, but they do have a thin outer coating of tin, which prevents the steel from turning to rust. Mercury is a special metal because it is a liquid at room temperature. This property makes it especially useful. For example, mercury can be used to make thermometers. Iron is one of the best-known metals. Unfortunately, as this iron spike illustrates, it rusts very easily. Rust is a substance which contains the elements iron and oxygen. Cadmium is a pretty metal used to make rechargeable batteries. Magnesium is a reactive metal. It might be surprising to you that as a metal, it actually can burn. A ribbon of magnesium burns with a bright light when placed in a Bunsen burner. Magnesium is commonly used in fireworks.
Non-metals really don't have much in common with each other, except that they are not metals. Most non-metals don't conduct electricity or conduct heat. They can't be shaped because they are brittle and break easily. Some non-metals, such as carbon and sulfur, are solids, while other non-metals are gases, such as hydrogen and nitrogen. Some non-metals are colorless, while others, such as solid sulfur, have pretty colors. Carbon exists in two different forms. As graphite, it is a black, slippery solid. As diamond, it is the prettiest and hardest of all elements.
Recall that Mendeleev arranged the periodic table in such a way that elements that are similar to one another are placed in a column. All the elements that appear in a column are called a family. For instance, the family in the first column are the alkali metals. They are soft metals that are easily cut with a knife. They also react vigorously with water. Here, a small piece of sodium is dropped into water. It dances on the surface because hydrogen gas is formed by the reaction. No two members of a family are exactly alike. For instance, sodium and potassium respond differently in a flame test. Sodium atoms produce a bright yellow color when put into a flame, but potassium atoms give a blue color. Flame tests can be used to identify which elements are present in an unknown mixture.
The elements fluorine, chlorine, bromine, iodine, and astatine are called the halogens. The best-known halogen is chlorine. It is the yellow gas used to keep swimming pools free of germs.
Another family easy to recognize are the noble gases. The first member is helium, which everyone knows is a gas lighter than air. Helium is invisible and is usually stored in tanks under pressure. The next member of the noble gas family is neon, which is used to make signs that produce a bright orange light. The noble gases are given this name because they do not react well with other elements.
You might be wondering about the two rows of elements that appear out of order at the bottom of the periodic table. Well, they are shown that way to save space. This is what the periodic table would look like with the two rows in their proper positions.
Recall that elements are substances made up of only one kind of atom. Although atoms are actually very complicated, we can represent them simply by wooden balls. Each element can be represented by a different color. Atoms have a habit of attaching themselves to other atoms. This model shows two hydrogen atoms bound together to form a hydrogen molecule. A molecule is a collection of two or more atoms attached together. We use the formula H2 to represent the molecule. A gaseous substance results when atoms form small molecules. The element hydrogen is a gas. A solid substance results when atoms form large molecules. For example, carbon atoms bond to each other, as shown in this model, to make a diamond.
Substances called compounds are composed of combinations of the atoms of different elements. For instance, carbon dioxide, the gas we exhale in our breath, is made up of carbon and oxygen. Here, a model drawn by a computer is shown. The carbon and oxygen atoms are attracted to each other. Its formula, CO2, tells us that one molecule of carbon dioxide is made up of one atom of carbon and two atoms of oxygen.
Water is a compound rather than an element, as Aristotle believed. Water is made of the elements hydrogen and oxygen. The formula for it is H2O, which means that one molecule of water is made up of two atoms of hydrogen and one atom of oxygen. The smallest possible amount of water is one molecule of water. This model shows many water molecules all bound to each other. It represents a solid, not a liquid. You were correct if you guessed this is ice.
Calcium carbonate, also known as limestone, is shown here on the right. It is composed of three elements: calcium, carbon, and oxygen, which are shown on the left. Notice that compounds bear no resemblance to the elements from which they are made. This model shows how the atoms are arranged to form calcium carbonate.
Much more could be said about the elements, their compounds, and the periodic table. Chemists spend their lifetime studying such things. Perhaps it will come as no surprise that living things, including people, are made of the chemical elements. For the most part, the elements of the human body are in the form of compounds. For example, our muscles are made of protein, and proteins are compounds composed of carbon, hydrogen, oxygen, nitrogen, and sulfur. A few of the elements present in our bodies are shown here. Admittedly, they do not look much like a person.
The purpose of this video was to give you information about the history of the table, the evolution of thought concerning elements as the building blocks of all things, and some understanding of how atoms and molecules interact to form new substances. This is Game 1 of the Discover That Element program. It features 20 of the best-known elements.
One by one, they will appear on the screen and give you a spoken clue about themselves. Your challenge is to guess their names and symbols.
Before the game begins, you will need a copy of the answer sheet. Each element has a number which corresponds to an entry on the answer sheet.
A copy of the periodic table should also be in your view, since some of the game clues refer to atomic numbers, atomic masses, and element families.
If you cannot identify the element at first, write down some notes about it. Perhaps you will be able to guess it at the end of the game. Good luck and have fun. Number 1. I started a rush to California in 1849. Everyone thought they would strike it rich.
Number 2. I produce a bright red-orange light if you pass electricity through me. I belong to the noble gas family.
Number 3. Oxygen is used to remove my impurities in order to produce steel.
Number 4. I can be used as a greaseless lubricant.
Number 5. I keep your swimming pool healthy. I am one of the halogens.
Number 6. I offer a hazardous way to fly.
Number 7. I am easily recognized by my color.
Number 8. When dissolved in alcohol, I am a good antiseptic.
Number 9. I gave my name to the U.S. 5-cent piece.
Number 10. Because I am a colorless gas, you cannot see me. My atomic number is 7.
Number 11. My plating beautifies and protects. I have an atomic mass of 52.00.
Number 12. Without me, we would have no transistor radios, video games, or computers. I gave my name to a valley in California.
Number 13. You can't last 5 minutes without me.
Number 14. Thanks to my density, I can take your bait straight to the bottom of the lake. I am a metal, yet I belong to the same family as carbon.
Number 15. I am a brittle, yellow solid used to make gunpowder.
Number 16. I make a great container for drinks, and I can be recycled.
Number 17. My lifting power is less than that of hydrogen, but I am much safer.
Number 18. I am a silvery metal, but when chemically combined, I make strong teeth and bones.
Number 19. I gave my name to a can, which I serve to protect. I am another metal in the carbon family.
Number 20. All that glitters is not gold.
That's it. Game 1 is finished. Take some time to review your answers. You should enter a name or symbol for each element. Make a good guess if you need to.
The moment of truth is here. Your teacher will give instructions on the scoring of the game. The 20 elements of Game 1 will now reappear and tell you who they are.
Number 1 was gold. Since ancient times, people have prized gold for its color and luster. The metal is usually found uncombined in nature. It does not tarnish, and it is easily cast or hammered into works of art.
Number 2 was neon. Most people call this a neon sign, but to a scientist, it is a neon emission tube. When an electric current passes through a glass tube containing neon gas, a brilliant red-orange light is emitted.
Number 3 was iron. Molten pig iron produced in a blast furnace is poured into a basic oxygen furnace. Here, a stream of oxygen gas is blown through the iron to reduce its carbon and sulfur content. The resulting product is steel.
Number 4 was carbon. Graphite consists of flat sheets of carbon atoms layered on top of one another. This structure causes graphite to be soft and to feel smooth. It is an excellent material for lubrication. Carbon also exists in the form of other solids. Can you name them?
Number 5 was chlorine. Chlorine is an oxidizing agent. This means it has the ability to chemically react many substances. It can be used to kill bacteria in drinking water or a swimming pool. In household bleach, it works to destroy stains.
Number 6 was hydrogen. The Hindenburg was the pride of the German dirigible fleet in the 1930s. 36 people died when it burst into flames at the end of a transatlantic flight. The tragedy convincingly demonstrated that hydrogen is too combustible for lighter-than-air craft.
Number 7 was copper. Copper is an excellent metal for making pots and pans. It is malleable, a good conductor of heat, and beautifully colorful.
Number 8 was iodine. To a pharmacist, an alcohol solution is known as a tincture. Thus, iodine dissolved in alcohol is tincture of iodine. The solution is an effective germicide when applied to cuts and abrasions.
Number 9 was nickel. Coins containing nickel are minted in countries throughout the world. In most cases, the coins are made of alloys containing more copper than nickel. The U.S. 5-cent piece contains only 25% nickel.
Number 10 was nitrogen. This bottle may appear to be empty, but it contains the element nitrogen. Since nitrogen is a colorless and odorless gas, you cannot see or smell it. Nitrogen is the 7th element on the periodic table, so we know that its atomic number is 7 and that each atom has a nucleus containing 7 protons.
Number 11 was chromium. Chromium is used extensively for plating steel. It gives steel a rust-proof coating with a bright shine. Periodic table lists the atomic mass of chromium as 52.00. This means that the average mass of a chromium atom is 52.00 atomic mass units.
Number 12 was silicon. Silicon crystals are sliced into thin wafers to make solid-state semiconductors for such devices as transistors, solar cells, and computer chips. Silicon Valley is in California. It's the home of several companies that make computers and other high-tech products.
13 was oxygen. Scuba divers carry tanks of compressed air on their backs. The air contains the oxygen which the diver must breathe. Oxygen is used by living organisms to obtain energy from the food they eat. The process is known as respiration.
Number 14 was lead. Lead has a density of 11.35 grams per cubic centimeter. Since it is much more dense than water, lead can be used to sink fishing bait. The family to which lead belongs is a bit unusual in that it includes both metals and non-metals among its members.
Number 15 was sulfur. Approximately 800 years ago, the Chinese learned to combine powdered sulfur, charcoal, and saltpeter to make an explosive mixture. And so, gunpowder was invented. The world would never be the same.
Number 16 was aluminum. Aluminum cans offer advantages not found in other beverage containers. They do not alter the taste of the product or shatter or rust. Best of all, they can be recycled into new cans.
Number 17 was helium. Because it is more dense, the lifting ability of helium is only about 90% of that of hydrogen. Wouldn't you rather ride in a blimp containing helium?
Number 18 was calcium. Calcium is essential in our diet for good health. We mostly get it from dairy products. The average adult body contains 2 pounds of calcium, mostly in bones and teeth. The calcium is chemically combined with oxygen, hydrogen, and phosphorus.
Number 19 was tin. The ordinary tin can is not well named, since it contains only about 1.5% tin. The can is actually made of steel, which is plated with a tin coating about 1/10,000th of an inch thick. The tin protects the steel from rusting.
Number 20 was silver. Silver is another metal which, like gold, has a beautiful luster, but it tarnishes more easily. Because of the high cost of silver, the silver dollars minted in the U.S. are no longer made of pure silver. They are only silver-clad. This 1986 special issue, however, is pure. It's worth considerably more than $1.
Those are the answers. Did you do well? Congratulations to everyone. We next present Game 2. It is a bit more difficult than the first game.
A few elements from Game 1 appear again, but most are new.
Along with an answer sheet, you will need a copy of the element data sheet, which lists some physical properties of the elements. Here we go again.
Number 1. I can be detected from my bright crimson flame test, and my density is 0.53 grams per centimeter cubed.
Number 2. I am the metal can of a zinc-carbon battery.
Number 3. Heating in a test tube causes me to melt. I change from a yellow solid into a red liquid.
Number 4. I am the only metal element which is a liquid. This means my melting point is below room temperature.
Number 5. I am the only non-metal element which is a liquid. I melt at -7 degrees centigrade. Look for me in the halogen family.
Number 6. This planet has an atmosphere which is mostly me. Some simple forms of life take advantage of that fact.
Number 7. My melting point is the highest of all metals. I can be heated until I glow brightly.
Number 8. I was discovered in 1898 and was named after the Latin word radius, which means ray.
Number 9. I am better known in the form of a compound than as an element. You can drink my hydroxide to relieve stomach upset.
Number 10. My isotope of mass number 235 undergoes a nuclear chain reaction which produces great energy.
Number 11. My excited atoms produce a bright light for city streets. In Latin, I am known as natrium, and my chemical symbol is derived from that name.
Number 12. I am the 5th member in a family of all gases on the periodic table.
Number 13. I am alloyed with platinum to make an industrial catalyst. My name in Greek is Rhodon, which means rose.
Number 14. I was known to exist on the sun before I was discovered on Earth. Incidentally, the Greek name for the sun is Helios.
Number 15. I have an isotope of mass number 60, which is used by doctors to fight cancer. My atomic mass is 58.93.
Number 16. One of my allotropes is red and the other is white. In the red form, my density is 1.82 grams per cubic centimeter.
Number 17. The heat from a burner can vaporize me. I am purple halogen.
Number 18. I am a synthetic element. I was named after Pluto, the 9th planet in the solar system.
Number 19. I am teamed up with nickel, a NiCad battery.
Number 20. I belong to a family on the periodic table known as coinage metals.
That's it. Game 2 is done. Review your answers. Make certain you enter a name or symbol for each element. A good guess is better than a blank.
The 20 elements of Game 2 will now reappear and tell you who they are. Your teacher will give you instructions on scoring the game.
Number 1 was lithium. The beautiful crimson flame test for lithium was observed in lithium compounds as early as 1818. Lithium metal has such a low density that it floats on water. Most metals, of course, sink.
Number 2 was zinc. The common flashlight battery is made of a zinc can. The can is more than a container. It is the anode of the electrochemical cell. The battery produces electricity. The zinc is oxidized. It is the negative terminal of the battery.
Number 3 was sulfur. Most substances do not change color when they melt, but sulfur is an exception. The yellow solid becomes a dark red liquid. The liquid is very thick or viscous. This is because its atoms are linked together into molecules which are long chains.
Number 4 was mercury. We usually think of metals as being solids. Actually, all of them do melt and become liquids if you heat them enough. Mercury is special because it melts below room temperature. So, it is a liquid. Incidentally, liquid drops are perfectly circular because they have surface tension.
Number 5 was bromine. Since bromine melts at -7 degrees centigrade and boils at 59 degrees centigrade, it is a liquid at room temperature.
Number 6 was nitrogen. The atmosphere surrounding planet Earth is about 4 parts nitrogen and 1 part oxygen. Since these gases are invisible, they cannot be seen from outer space. Our bodies make no use of the nitrogen in the air we breathe. Some bacteria, however, convert it into useful compounds.
Number 7 was tungsten. Its high melting point makes tungsten an ideal metal for light bulb filaments. When electricity passes through a thin tungsten wire, the wire becomes hot and glows brightly. It is incandescent.
Number 8 was radium. Marie and Pierre Curie succeeded in isolating about 1 gram of the element radium from about 8 tons of a mineral called pitchblende. The new element emits radiation, which we cannot see, but which can be detected with instruments. The Curies named the element for this special property.
Number 9 was magnesium. Magnesium is a silvery metal commonly sold in the form of a coiled ribbon. On the other hand, magnesium oxide is a compound of magnesium and oxygen. It's a white powder which can be mixed with water to produce magnesium hydroxide. The mixture is an antacid. To a druggist, it is milk of magnesia.
10 was uranium. The uranium isotope of mass number 235 undergoes a nuclear chain reaction. The nucleus of the atom splits apart and 2 smaller nuclei are formed. This reaction, known as fission, produces much energy. Energy can be used to make electricity for people or weapons of mass destruction.
Number 11 was sodium. Streetlights which emit a yellowish light contain sodium vapor. Sodium atoms emit the light when they're excited by heat or electricity. Some elements have symbols based on their names in a language other than English. The symbol for sodium is Na, which makes good sense in Latin.
Number 12 was xenon. Xenon is the 5th member of the noble gas family. The family is located at the right edge of the periodic table. Its members are called noble because they are reluctant to associate with other elements and make compounds with them.
Number 13, rhodium. Rhodium is combined with platinum to make a catalytic gauze used by the chemical industry. The gauze increases the rate of the reaction, which converts ammonia into nitric oxide. The element's name comes from the fact that some rhodium compounds are rose-colored when dissolved in water.
Number 14 was helium. Helium is the only element known to exist on the Sun before its discovery on Earth. In 1868, astronomers made a spectroscopic study of the Sun's corona. A yellow line was found in the spectrum which did not belong to any element known. The new element was named for the Sun.
Number 15 is cobalt. The cobalt isotope with mass number 60 is radioactive. Its nucleus emits gamma rays which can destroy living cells. Doctors take advantage of this fact when they use cobalt-60 to defeat cancer in the human body.
Number 16 was phosphorus. Phosphorus is an element which exists in more than one allotropic form. Each allotrope has its own properties. Red phosphorus is stable in air, but white phosphorus is so reactive with air that it must be stored underwater.
Number 17 was iodine. Iodine is the 4th member of the halogen family. It is a solid at room temperature, but a bit of heating causes it to become a vapor. When a solid becomes a vapor directly without first becoming a liquid, we say it has sublimed.
Number 18 was plutonium. All elements heavier than uranium are synthetic. Although they are not found in nature, they can be synthesized in a nuclear reactor. Plutonium is an example. It is made by bombarding uranium with neutrons. You might say that the dream of the alchemist has come true.
Number 19 was cadmium. Cadmium is a silvery metal which is more chemically reactive than nickel. The two metals are used to make rechargeable nickel-cadmium batteries. When the battery discharges, the cadmium is oxidized to cadmium hydroxide.
Number 20 was copper. Copper has been used to make coins since ancient times. It belongs to the coinage metal family on the periodic table. The other members are silver and gold. The three metals are not very chemically reactive. After all, if you put a coin in your hand, you do not want it to react. Now you know them. How well did you do on Game 2?
Congratulations to everyone!
Your discovery of the chemical elements is now complete.
We hope you enjoyed the experience. As you go through life, the elements will never be strangers to you. After all, you are made out of them.